So this talk will probably have more in common with Professor Kim's talk than with some of the other talks. Okay, it's going to be a little survey of aspects of the strong CP problem, different kinds of solutions, different, why, and I'm going to focus, I should say, on the axion as a solution of the strong CP problem. So, okay, so axion-like particles arise in various contexts, and of course that's been a sort of underlying theme here. Today I'm going to focus mainly on axions which arise as solutions of the strong CP problem. And this allows us to somewhat narrow the possible theoretical issues, phenomenologies, and cosmologies. So in outline, I'm going to talk briefly about the strong CP problem in general. I'll discuss three solutions of the strong CP problem. There are really probably others, but I think there are three principal solutions, and I'm going to try to give some assessment. And I'm going to argue, not that strongly, but I'm going to argue that the axion, while it has warts, is the most plausible of these. Then I'm going to talk a little bit about theoretical issues involving the Pache-Quinn symmetry, the axion idea. And I'm going to talk about possible values of the Pache-Quinn scale and some corresponding theoretical issues. And I should say that I will talk in particular about some alternative cosmologies to those which we frequently discuss in this framework. Okay, so all of us are well aware that we can add to the QCD Lagrangian a term, L theta is theta over 16 pi squared FF dual. Okay, this term violates parity and thus CP. And while FF dual is a total derivative, FF dual is partial mu of, let me see if I can get this to work yet. Oops, no. Is partial mu of some current. This current K mu is not gauge invariant. And if there are important configurations, say in the path integral for which the A cubed term falls off like 1 over R cubed, okay, then we can't drop the corresponding surface term. And instantons, okay, while they don't provide a reliable calculational tool, okay, do provide evidence that, in fact, there are such contributions. Okay? Now, if the absence of a ninth light Goldstone boson is accounted for by the anomaly, okay, then theta FF dual has real physical effects. And indeed, from SU3 cross SU3 current algebra, a current algebra absent the ninth Goldstone boson, one can compute the electric dipole moment of the neutron. Okay? And the neutron electric dipole moment calculation constrains theta to be less than something like 10 to the minus 9. And this raises a puzzle. Why is there such a small dimensionless number? And this is the thing known as the strong CP problem. Now, as theta goes to 0, strong interactions preserve CP. So if not for the fact that the rest of the standard model violates CP, this would be natural. But it's not, okay? Because the standard model does violate CP. Okay? And one of the things that I sort of think about in this context is among naturalness problems, the strong CP problem is special in that it is almost of no consequence. Okay? That compares with the cosmological constant. If the cosmological constant was a few orders of magnitude larger than observed, the universe would be dramatically different. And the same is true for the value of the weak scale and the values of the light quark and lepton masses. But if theta, say, were not 10 to the minus 10 or smaller, but say 10 to the minus 3, nuclear physics would hardly be different than we observe. And since effects of theta are shielded by, since effects of theta are shielded by small quark masses. So it's hard to imagine, for example, an anthropic solution. Okay? You may not like anthropics, but it's not even clear how you would implement such a thing. So there are various possible resolutions of this puzzle, and I'm going to focus on three, which I sort of view as the three principal ones. Okay, so one of those, which was suggested early on, was perhaps the bare U quark mass is 0. Okay? If true, then a chiral rotation of the U quark field would eliminate theta from the Lagrangian, and an effective MU might be generated from non-perturbative effects in the theory. Okay, so initially people thought about this by thinking about instanton contributions, but you can phrase this more generally in terms of possible operators in a chiral Lagrangian, as is done by Kaplan and Manhart. And this massless U quark might result, for example, as an accident of discrete flavor symmetries or a result of anomalous discrete symmetries as arise frequently in string theory. Okay, so that's one possibility. Okay? A second possibility is that CP is an exact symmetry. Okay? Microscopically, it's exact, theta equals 0, but it's spontaneously broken. And that gives rise to the CKM phase and leads under suitable conditions to a small effective theta. So this is an idea due to Ann Nelson and Steve Barr. In critical string theories, CP is an exact gauge symmetry, spontaneously broken at generic points in a typical moduli space. So that's one setting in which this kind of idea, this idea of spontaneous CP violation as an explanation of the strong CP problem might arise. And the third, which of course is the focus of this workshop, is that there might be a new light particle called the axion, which dynamically cancels off theta. So each of these solutions has its problems. Okay? So mu equals 0 is problematic for several reasons. Most dramatically because lattice computations seem to rule out the required non-perturbative, to rule it out, excuse me. So in other words, the required non-perturbative effects do not seem to be large enough to account for the effective mu that we see. And you can also make these arguments, arguments based on large n. So to the extent that large n is reliable in QCD, you can also show that that mu can't be 0. So this idea, while very intriguing, has its problems. Okay? A second is this spontaneous CP violation. Okay? Generically, when you break CP spontaneously, okay, you generate a large theta. Okay? So to avoid that, you need to go through some model building acrobatics. I'll kind of illustrate that very briefly in a few minutes. Okay, and then the question: these theories don't look particularly generic or anything. So why would nature go to so much trouble to hide theta? Okay. And then axions, and I'll spend more time on the promise and limitations of axions. So let me just summarize the lattice results for light quark masses. Mu, according to the flag summary of lattice gauge results, is 2.16 plus or minus 9 plus or minus 7 MeV. Okay. MD is 4.68 with some error bars, and MS is 93.5. And these numbers are quoted in the MS bar scheme at about a scale of 2 GeV. So mu is many standard deviations from 0. Okay, and as I said, also large n also rules this out. This is probably the end of the story, but there are some proposals for dedicated tests of the lattice results and calibrations of these lattice results. But I really think that it's very unlikely that anything in this will get upended. Okay? So let me talk a little bit now about this Nelson bar structure. Okay? So a simple realization, which is basically the one that Nelson and Barr wrote down, is that suppose you have, in addition to the normal quark doublets and d quark singlet, you have an extra q bar, okay, with a vector-like quark with charge 1/3, okay, where phi is the Higgs here. Yes, phi here is the Higgs. And y, lambda, and mu are real because of our assumption that the theory is CP conserving. Okay, and then the mass matrix for the quarks looks like this. It looks like it has this diagonal term and a 0 and an off-diagonal term. Okay, here B comes from this lambda f eta I. Eta I is now the expectation value of this field. Okay, and M has a real determinant. Okay, so this concoction gives you a 0 theta at the tree level. Now, but there are a number of requirements for this that you have to satisfy for this to work. So, for example, it's important that this field eta not couple to q bar. Okay, so for example, the etas might be complex subject to a Zn symmetry. Okay, you need some coincidences of scale. If there's only one field eta, the CKM angle vanishes. You can make the d quark mass matrix real by an overall phase redefinition. And so you need to have at least two, and their VBEVs times suitable coupling have to be quite close. So the CKM angle in particular is sort of the ratio of a smaller b, this parameter b, to a larger one. Okay, this can't be this can't be extremely small, or we won't have a suitable CKM angle. CKM angle is not particularly small. Similarly, mu, which might represent the Bev of another field, this was this parameter that appeared before, cannot be much larger than eta, and if it's much smaller, the Yukawas and B's have to have special features. So all of this is to say that the Nelson-Barr solution is not particularly generic and requires some model building acrobatics. Okay. And one could say more about all this, but just to give some flavor. Okay, so finally, my personal view is that both the mu equals 0 and the Nelson-Barr solutions are disfavored. Okay, and so I want to focus then on the axion. So in a somewhat streamlined language, the Pache-Quinn proposal was to replace theta, okay, the parameter theta, by a dynamical field, A of x over Fa. And it's assumed that A goes to A plus omega Fa. Okay, so omega is Fa is the decay constant of the axion. Omega is a symmetry parameter, is a good symmetry of the theory violated only by effects of QCD. Without QCD, theta can take any value. In QCD by itself, the energy is necessarily stationary when theta effective is A over Fa equals 0, and this is simply because Cp is a good symmetry of QCD if theta equals 0. So the vacuum energy or potential must be an odd function, must be an even function of theta. So in some sense that sort of gets you started with the statement, why does this work? Why does this axion solve the strong CP problem? It's this fact that absent other effects, okay, the axion potential is an even function of A, and so it has a min at the origin, or a stationary point at the origin. Now one can do better, calculating again using what we know about chiral symmetry in QCD, the axion potential, and one gets V of A to quadratic order in A is m pi squared f pi squared and I'm treating this as a world of two light quarks, square root of mu md over mu plus md, A squared over 2fa squared. And this gives for the axion mass ma as 0.6 millielectron volts times 10 to the 10th GeV over Fa. Okay. Now, Pache and Quinn, as Professor Kim mentioned the other day, Pache and Quinn actually constructed a model of this phenomena, which is a modest extension of the standard model with an extra Higgs doublet. They didn't phrase the problem in quite the way I did above and didn't appreciate that their model had a light pseudoscalar particle. This was recognized by Weinberg and Wilczek, who calculated its mass by basically writing the formula I wrote before and the properties of its interactions. And it quickly became clear that the original axion idea was not experimentally viable. Okay, and I can date myself by saying I listened to Weinberg give a seminar as a graduate student on this topic, and people in the audience raised their hands and said, "What about beam dump experiments?" Okay. But allowing for a larger decay constant and a lighter axion evaded accelerator constraints. So this is this invisible axion. Avoiding astrophysical problems placed a lower bound on the decay constant of order 10 to the 10th GeV. And early examples of models of this type go by the names KSVZ, of whom we have an author here, DFSS, but the phenomenon is... Sorry? Oh, yes. Yeah. Okay. But in any case, this phenomenon is generic. If you raise Fa, you make the axion lighter and you weaken its interactions. Okay. And so for a range of Fa, for Fa large enough, okay, you suppress problems with astrophysics. Okay. And as you know, if Fa is too large, okay, at least within the standard cosmology, you produce too much axion dark matter. So I want to talk a little bit about the question of axion quality. Okay? So this is a theoretical question. Why are there axions at all? Okay? More precisely, why should there be a Pache-Quinn symmetry? and how good a symmetry does this have to be? Okay. So there's a general belief, supported by studies of string theory, that a theory of quantum gravity does not possess exact global symmetries. Okay, so why is this thing there? So is it hopeless? No, the symmetry might be an accidental consequence, for example, of other symmetries. And for example, if you have discrete symmetries, if I have a field phi, okay, whose phase is going to be the axion, for example, phi is, which transforms under a discrete symmetry, phi goes to phi e to the 2 pi I over n, okay, then if n is large enough, okay, then the leading symmetry breaking operators, just in terms of phi, go like phi to the n over mp to the n minus 4. So by this I mean the leading operators which violate the approximate continuous symmetry. Okay, so we get an approximate symmetry violated by some high dimension operators. Okay, and I'm just assuming that these high dimension operators come with factors of n Planck, If they come with smaller factors, what I'm going to say is even more troublesome. Okay? So if n is large, these terms would be very small, but they have to be extremely small to ensure the smallness of theta. So one needs, for example, that the term linear in the axion, okay, be such that gamma over ma squared was less than 10 to the minus 10 fa. And this translates into a requirement that n be greater than 12 if fa is 10 to the 11th, and even larger for large a. So remember, n is the n of this Zn symmetry. Okay, so you have to have something like Z12. Okay, why Z12? Okay, well, could be, okay, but it's not. It's certainly disturbing.
Do we need a Z12 as gauge, or is it also global?
The symmetries typically, for example, when as I said, in string theory, you don't get continuous global symmetries, exact continuous global symmetries. Okay, you do get exact discrete symmetries, and those can usually be understood as gauge symmetries. Okay. Okay. So axions from the perspective of effective field theory are surprising. It has long been known, however, that axions are common in string theory, and indeed axion-like objects seem in some sense ubiquitous. Okay? The corresponding Pache-Quinn symmetries are typically good to all orders of perturbation theory. Okay? So if the couplings are weak, then the symmetry violating effect should be exponentially small. Okay? So this is something, so basically I'm just saying that if there's some coupling G in the string theory, let's call it GS, then the symmetry violating, let me write it this way. Symmetry violating terms will go like exponent sum minus b over gs squared. Okay? And if gs is small, this could be quite small. Now that opens another can of worms, which I won't talk about. Okay? But why should GS be small? Is it sensible that GS be small? But at least gives a framework in which we can discuss this, and in which axions, as I say, appear to be common. Oops. Okay. So, all right. So I want to turn to a different subject, okay, which is the standard computation of the axion dark matter density. So I'm not going to review that here. I mean, I think you're all pretty familiar with it. Okay? But in recent years, a number of questions have been raised, including by people in the audience here, about the reliability of the standard computation of the axion dark matter density. And I don't have time to review these thoroughly here, but they will be subjects and are subjects of discussion at this workshop. And here I'm going to just list a few and express my own views, and you can take that for what it's worth. Okay? So if a Pache-Quinn transition occurs after inflation, okay, which is where one gets this limit, so if I have a post-inflationary so this is kind of the standard picture for the dark matter. So Fa, something like 10 to the 12, maybe 10 to the 11 GeV gives the dark matter. And it is, and as we've seen, and I think a number of people here are working on, axion cosmic strings have arise in this context, okay? And they have an infrared divergent tension, and they carry a great deal of energy. And so in fact, a way of saying this is that there's a parameter, which is often written as xi, which is something like log Fa over h. Let's call it the Fa of h of the transition. Okay? And this number can be large. This number can be 80 or so, I think. Okay? And this is a large parameter which might, and has been argued, might affect the dark matter density in ways that would have profound implications for experimental searches, for example, for axions. Okay? Now, my claim is that this infrared divergence, and this would be a subject of another talk, it is the subject of another talk, implies that strings can't be considered in isolation. So typically what is one trying to do with, sort of theoretically with strings? One's trying to describe a system in terms of some set of collective coordinates, okay, the coordinates which describe the string, okay, but one can't describe that in isolation. That's what infrared divergences generally signal, that you need to include other degrees of freedom in your description. Okay? So we need to include low momentum axions as well. And in fact, and when you consider that problem, it would appear that the extra energy that you have, the energy associated with these short wavelengths axions, okay, gets dumped into high momentum axions, okay, which don't contribute to the dark matter density. Now I realize this is not a statement that's going to go over well with everybody, so I'll just leave it at that, and we can argue about it over the rest of the week. Oops. Okay. Now, it has long been recognized that the underlying cosmological assumptions of the standard calculation of the dark matter density don't have to hold, and that there is good. And from what I said about string theory and axions, there's good theoretical motivation to consider lighter axions with larger decay constants. Okay? So, for example, if there is an underlying supersymmetry at some high scale, it doesn't have to be a TeV scale, then there is a particle, the axion, the scalar partner of the axion, okay, and it's which leads to even more severe problems with cosmology than the axion. Okay, and solving those requires something new. Okay, so typically one tries to solve that by assuming some significant additional entropy production through some other light fields, the decays of other light fields, okay, at a relatively late stage of evolution. And in such a picture, the universe was likely never hotter than about 10 MeV. Okay, so the standard computation, which assumes that we basically start near the QCD scale, okay, doesn't hold. Okay, so this is so string theory in particular, as I've said, might be a setting for the axion. Okay? If there's an exponentially small parameter, okay, in that theory, so for example, accounting for hierarchies, this parameter might explain why the Paget-Quinn symmetry is a necessary quality. Okay? And one thing I want to claim, I should say this notion of the importance of axion quality goes back a long way, but the word I want to claim credit for. Okay. So, oops. Yeah. Okay. So, string theory is suggestive of a modified cosmology and a higher FA. Okay, it doesn't have to be. String theory might support a lower FA. String theory might have nothing to do with anything. Okay, but still, it's suggestive. Okay. So overall, then, I would say the axions are quite natural in string theory, and large decay constants might be consistent with cosmology. And detection of such axions is clearly a challenge. Detection of standard axions is obviously quite a challenge. And this has been recently pursued by a number of people, including Peter Graham and Sumir Rajendran and others. So I'm going a little faster than I thought I would, so I'm happy to have entertained some discussion. So I'd like to sort of say what's my outlook. Okay? So axions are a well-motivated dark matter candidate. Okay? And I think what I tried to suggest is that in some sense they're the best well, they're not, they have their issues. They're, at this point, the best motivated candidate. The most straightforward approach, the standard approach with the standard cosmology, where the universe starts out at a high temperature, suggests that they should be detectable in cavity experiments. Okay? Okay. Theoretical arguments, though, suggest that in a more complete cosmology, axions might be lighter, and that's referring here to the story of string axions. And in either case, their detection and study would be an extraordinary development. Okay, so that went much faster than I thought it would. So I'll stop there and entertain questions and discussion. I assume the applause is because we're quick. Yes.
This is a very clear overview, very nice, thank you. And there is time to discuss. We have some questions, comments. Sebastian.
Yes, sorry, so you, I just saw that you flicked through the slide with the domain walls. What was the point?
Oh, okay. So this is actually something I'm thinking about at the moment. Is this the function as eraser?
Yeah.
Okay. So, okay. So domain walls are a long-standing problem in these post-inflationary axions. If this so-called parameter, this parameter n, is greater than 1. Okay, there are other issues if n is equal to 1. Okay, but I'm going to focus on n greater than 1. Okay, and what in particular happens is that you have some. So what this means is that you have. I talked about one Zn symmetry. This is another. Maybe I should call this script n or something just to distinguish it from what I had before. Okay, so so one has a Zn symmetry. This is in the limit that only QCD axions, only QCD effects, violate the Pacheco-Quinn symmetry. Okay, and this Zn symmetry gives rise the spontaneous breaking of this symmetry. Gives rise to domains. Okay, so you have some so this phi in particular that characterize okay, can take different values. And in different domains. Okay, and those domains are separated by what are called domain walls. Okay, so this is a point I think was first made by Sakibi. So I have sort of draw them. I don't know how to draw them really. So I have +3 - 2, depending what n is, +1. Okay, different domains. Okay, separated by walls, and these walls, if nothing else happens, come to dominate the energy density and spoil the standard cosmology. Okay, so various solutions have been proposed to this. One is perhaps n = 1. Okay, another is that, in fact, the violations of the Pacheco-Quinn symmetry lift the degeneracy among these vacua. And I probably should draw one more. Let me put 0 here. Okay. And say everything, and so all of these collapse except the lowest energy state, which I'll call 0 here. Okay. So and you can ask what happens to these regions. Okay. And in fact, these regions, as they collapse, radiate little axion, little of their energy into axion. Or other things, gravitational waves, electromagnetic waves, and so on. Okay, so most of the energy is converted into kinetic energy, and the walls become ultra-relativistic. Ultra-rel, I can't spell, relativistic when they disappear. So most of that energy, where does that go? Most of that energy goes into ultra-relativistic axions. And those axions are, provided you've arranged that this happened before the domain walls dominate the energy density, the fraction of the energy density in the universe in these ultra-relativistic axions is not large, and they're relatively harmless. Okay? So that's really sort of what that story is about. Okay? So there have been arguments in other directions about this, and I'm sort of disputing those.
Okay, in this case, I think we have a certain upper limit in the size of these vibration.
Yes.
If you don't want to lose this natural patching, you can solve this without any time tuning.
Yeah, no, okay, yeah, I could talk about that too. I could talk about that too. So basically, so one way to say this is I said that you need n equals 12 or something like that in terms of this Zn symmetry. Okay, but now you ask, okay, let's now require that the breaking not be too small, so that the domain walls don't come to dominate the energy density of the universe, and the 11 or 12 becomes 13 or 14. You're in some very narrow range of possibility. You have a very narrow. I don't quote me on the number. I claim there exists a range of parameters, but it's small. So
the point is that you leave the generalization big enough to make the domain ones
right. While keeping theta small enough. Absolutely. So that's a problem, and and in the paper, which I may or may not put out on this topic, on this whole set of topics, I said, well, the only thing that I can, I started out by saying I don't know how to invoke the anthropic principle for axions. Here, there might be an anthropic argument that constrains you to this range, and I don't have better than that. It looks ugly.
Or you can stay you inflate the universe where you was taking.
Oh, well, this is all for the post-inflationary. So I should say, by the way, I'm a much bigger fan of the pre-inflationary view, but it's sort of so the pre-inflationary view is sort of that story that I talked about in string theory, for example, where so in string theory you have those axions in front of you sort of from the beginning. Okay, inflation happens later. You need this production of entropy later. Okay, sort of if you like, the reheat temperature is very low, and I'm more of a fan of that story personally, but I believe in a certain sort of self-discipline. I work on things I don't like.
So when you really add in let's say you add in a Z6 gauge symmetry, do you break the fundamental string solution? I mean the cosmic string solution so that they already solve the domain wall problem? For T6 or T12, it's already the angle is not 2 pi, it's actually 2 pi to the end, so that your fundamental string is like a hybrid string or something.
Yeah, I have to think about that a little bit. It's a good question. I don't know if I got a quick answer for you. It's a good question.
Can I have another question?
Of course.
So you talk about larger and solve the can exclude mu equal to 0. Can you explain more detail?
Well, yes, I'm not really prepared. I did this a while ago, so I'm forgetting various details. But the basic idea is in large N, you can enumerate the operators in the chiral Lagrangian, which are leading order. And there's only a small number. So you fit those. You ask where this Kaplan-Manohar fits in that story, and it's too small. So it's basically the idea of systematically enumerating the terms in the chiral Lagrangian in the order in N.
Is it similar to using larger N to solve the inner problem?
Sorry?
Is the same logic to using a larger N to solve the inner problem?
Yeah, it's similar to that. Any questions?
You were going over other slides also very quickly. I've seen the slides.
What's it? Say again? I'm sorry.
You were going over others. There were other slides over which you also went very quickly.
True.
But we did.
But so you're welcome to, I'm happy to go back to anything if people would like.
How much do you think, if you want to go back to quality problems, right? You
Yeah.
mentioned it. Do you think it's a very important issue now? Because that selects, it's a good selector for models.
Well, I think it's yes, it's a selector for models. I think it's a very important issue. I say I kind of had this, I talked about these three solutions of the strong CP problem, and I sort of hierarchically arranged them in terms of things which are more or less plausible. So unless you really seriously question both the large N and the instantine calculation, mu equals 0 is just ruled out. The Nelson Bar story is really okay if you're willing to live with a lot of complexity, okay? And the string theory story, the axion story is in some sense not better if in the conventional form, if I really need this large Zn symmetry. So large Zn, so it's really, I think my sort of fondness for the axion story in part hinges on this fact that in string theory, these axions seem to be, there's some sense in which they're generic, in which you don't have to stand on your head. I should say, you do have to stand on your head to explain why in string theory you would have a weak enough coupling to explain this hierarchy, but at least somewhere in the space of theories you know about, these ideas are implemented. You don't have a lot of, given your starting point, you don't have a lot of additional theoretical gymnastics.
But it's funny because historically, the Weinberg-Witzek axion didn't have the polypro, right? But because it was heavy, so but then obviously it was excluded.
Yeah, so people, right, so people like Kamiankowski.
Well, it has a problem because if you write an operator dimension 1, there is a problem. It doesn't
So
have
various
a
people
problem
pointed
only
it out.
If you have operators of dimension higher than 4, but nothing impedes you to write a...
My memory is somewhat feeble, but I think with the appearance of indivisible axions, I believe it was Howard Georgi who actually first pointed out some version of this quality problem, and then there were March Russell and Kamiankowski and others who made it very sharp.
But I also have a question.
Sure.
Before you wrote there the exponential of minus inverse coupling constant. So that's a non-perturbative effect.
Right.
So you believe that gravity is giving the type of a violation of the global, even if accidental, of the global symmetries?
Yes. Well, so why do I believe that? So I don't have a reliable way of doing that calculation in string theory, okay? But roughly speaking, there are things like instantons in the theory and so on, which look like they would break the symmetry. So it's not better than that. I don't have a sharper story than that.
Gravitational wormholes,
For example, yeah. Yeah, absolutely. Right. Okay. So I just would conclude by saying well, believe in axions is a little strong statement, but I think axions are quite plausible. But where they sit in the space of possibilities, that's are they in this large FA region? Do we need some modified cosmology? Do we need to think about other kinds of detection strategies? Do we need to think about other cosmological and astrophysical elements? That's possible.
Right. Okay, I guess
Okay.
maybe we stop here.
Okay, thank you, everyone.
Comments or questions